Hi everyone, today's lesson is on similar polygons. So let's get started. We're going to start off with dilating a triangle. We're going to call that triangle ABC. So the first thing we're going to do is we're going to draw the points for the triangle. So we have 1, 0. So here's 1, 0. Then we're going to call that A. And then we have B, which is 2, 2. So here's B. And then we have C, which is 3, and then -3. So there's C. So we draw this triangle. And what our objective is to dilate it by a factor of 3. And in doing that, when we dilate to a scale factor of 3, we're going to basically multiply all of these values by 3. So we're going to have 3, 0. We're going to have 6, 6, and we're going to have 9, -9. And so my new triangle is going to have values 3, 0. We call that A prime. Then we have 6 and then 6, and that's B prime. And then we have 9 and then -9, and that's C prime. And so if we connect that, the endpoints and the vertices, here you go, then what you have is a dilation. So what that means is it expanded by a factor of 3. We call that a scale factor. So what transformation maps each purple triangle into a yellow triangle? So, and then a different question is the transformation in isometry? First of all, taking a value, a shape, and moving it to the right or left or up or down, that's what we call a translation, okay? Taking this kind of graph and you have expanding it or you're shrinking it by a certain scale factor, we call that a dilation, just similar to what we just did. But whether or not something is an isometry is basically saying, if you move it, does it retain the same size and shape? And so if it does, then it's isometric. So this one would be a yes, because when we translated the triangles, we ended up getting the same size and shape. Whereas for this one, the dilation actually changes the isometry. So this would be a no isometry, and the other one would be a yes. So today's lesson is mostly about similar polygons. And if you notice, we have some similar polygons. This is where our corresponding angles kind of line up like this, where we have this angle corresponds to this one, this angle corresponds to this angle, and this angle down here will correspond to this angle right here. So for two triangles to be similar, they do need to have angles that are the same value. Now the sides do not have to be the same value. Sides are going to be what we call proportional, but the angles are going to be congruent. So that's kind of important. So the angles are congruent, but the sides are proportional. Okay, so you should write that down. Okay, so congruent polygons. So if you have two polygons that are congruent, they're not technically well, they're congruent. So the angles are already the same and the lines are the same. See, and so basically these two triangles, this shape right here, it is congruent. Okay, so these are two congruent polygons. All right, congruent. But similar polygons have the same angle measurements, but they have different side lengths. And the side lengths are what we call proportional. So meaning I could say large to small, and that's going to be, I'm comparing these two sides, 4 to 2. So 4 to 2, that has a dilation, and I'm shrinking of 2, scale factor 2. So we actually call that a scale factor. I can also compare large to small. So I can say 3 is to 6, and that's going to be equal to 1/2. Okay, so you have scale factors depending on whether you're going large to small or small to large, okay? Okay, nothing there. So we have similar figures. And a couple chapters ago in our geometry books, we covered corresponding parts of congruent triangles are congruent. That's CPC-TC. Two polygons are similar if their vertices can be paired such that, number one, as we just talked about, the corresponding angles are congruent. The angles that correspond with each other have to be congruent. But number two, the sides have to be proportional, meaning the sides have to be the same ratio. And if I were to compare these two, I can say either 4:2 as left is to right, as left is to right, as 6:3. And if I were to cross multiply, I would get 12 is equal to 12. Likewise, I could also compare height is to width as height is to width. So if I said 4:6 as 2:3, and these should equal. And I could check that by just cross multiplying, and I get 12 equals 12. So your sides, again, have to be in proportion, but your angles have to be congruent. And this is for two shapes to be similar. Now, squares are similar because the sides are always going to be equal and in proportion. Likewise, the angles are all congruent. So if squares are similar, the answer is yes, always. Okay. But a lot of different examples occur when you are checking this, like you're comparing shapes of like a miniature. So like if you've ever been to Disneyland, you've seen this. This is like a miniature. Disneyland has a lot of miniature shapes. And this is a miniature of, the actual, when you walk inside of Disneyland. Whereas, see that if you were to compare these, this is you walking into Disneyland. So if you're farther away, obviously this is looking smaller, but the closer up you are, it looks bigger. Likewise, this is the Matterhorn. This looks very large when I'm up close, but far away, it's like a perspective, okay? Now, the two objects are similar. They have the same shape. They have the same angles, but, they're proportional. The sides are proportional, and the two shapes are similar. So we have what's called a scale factor. Now, the scale factor basically is the ratio of length of two corresponding sides of two similar polygons. So you're not going to find, so like if I have a triangle like this and this, if I said this was 5 and this was, let's say, 11, the scale factor would be side compared to side. So it would be 5 to 11. So that would be my scale factor. You compare two sides, two corresponding sides. I wouldn't, if this was, let's say, 12 down here, I'm not going to say 5 is to 12. I'm going to say left side is to left side. So what I want you to do here is I want you to look and see, read the directions. The directions say that triangle ABD, so this triangle right here, is similar. This little enye right here, that means similar. So ABD is similar to ACE. So for these two shapes to be similar, then they have to have corresponding angles, which they do, right? If I were to peel off ABD, let's do that actually. So let's do that. So we're going to peel off ABD. So here's A and then B and then D. And then I'm going to still have the larger triangle below, okay, which is A again, and then C and then E. And so what I want to do is peel that off and put my values in. So then we know this is 5 and this is 6. This is the sides of the little triangle. And then my base is 3. But then the length of the side of the larger triangle, that's going to be y plus 5. And the length of the side of the right side is going to be 10. And the base right here is x. So what your job is to find x and y. Now we're assuming that these are parallel. And in that assumption, these angles would be the same because they're corresponding angles. We already know that this angle is the same because angle A is going to be congruent to angle A. But by stating that these two triangles are similar, that is saying that the sides are going to be proportional. So for the sides to be proportional, then that means I can make two ratios for each of the sides. So the first thing I want to know is what's the scale factor. So I can't say that my scale factor is 3 to x because I actually need to compare two sides. I need side to side, and I need to know those values. And I can't say that my scale factor is 5 to y plus 5 because, again, I don't know this length. But I can say that my scale factor is 6 to 10. Okay, so when I'm talking about 6 to 10, I'm going to reduce that. And so if I reduce that by 2, I'm going to get 3 is to 5. And so that scale factor is 3 to 5. And keep in mind, you see how I wrote this, ABD to ACE? That means I'm going small to large. So now for me to find x, okay, I'm going to make a proportion. I'm going to say, well, in order to find x, I need to go 3 is to x as 6 is to 10. See? 3 is to x as 6 is to 10. But I already know 6 over 10 is 3/5. So actually, I just have to rewrite that. And obviously, x is equal to 5. Now, most of the time, what we're going to do is we're going to cross multiply, meaning we're going to go 3 times x equals 15, and then divide by 3 on both sides, and I get x equals 5. But sometimes, sometimes you just get one of these, questions where you're like, oh, if the numerators are the same, then the denominators have to be the same. They're equal. Okay, so that's x equals 5. So now for me to find y, I'm going to go, okay, 5 is to y plus 5 as 6 is to 10. Again, see, 5, left side is to right side as 6 is to 10. Okay, and then by doing that, I have to say as 3 is to 5. So I'm going to cross multiply, and when I do that, I'm going to get 3 times y plus 5 is equal to 25. 3y plus 15 equals 25. 3y is equal to 10, so y is equal to 10 over 3. And so that's what y equals, and then that's what x equals. Now, I do want to just say that there is actually one other way that when you have a triangle like this, that where it's like on top of each other like that, you can do this. This is not going to give you your scale factor, but you can use this as a ratio, and you can go this side is to this side as this side is to this side, and that's actually going to give me y, meaning I can go 5 is to y as 6 is to 4. I'm going to cross multiply 6y equals 20. I'm going to divide both sides by 6, and I'm going to get y equals, divide by 2, 10 over 3 again. So it's just like another option that you can use if you like. Personally, I always separate my triangles. I think it's a little bit easier to see what actual sides you have and what you're trying to find. So these two trapezoids are similar. So I'm telling you that they're similar. So remember, this little enye means similar. So again, I personally, like I said, I like to separate my shapes. Okay, I think it's easier. I think it's easier to see what we're doing, and that's my preference. So I'm going to do that, and now I'm going to put in all my sides. So I know that this little bottom here, so these are my right angles here. Okay, I know that this length here is 10, so that's 10. And that's z, that's from here. I know this is y, and I know that's x, because that's that length here. Now, on this side, I know that's 12. I know that's 16. This whole length here is 15, so that's 1, 5. And my base is going to be this whole length here, which is 10 plus 14, and that's going to be 24. So remember, when I'm finding my scale factor, I have to have two sides that I actually know. So I can't use my scale factor as x is to 15. I can't say y is to 16. I can't say z is to 12, but I can say 10 is to 24. So for my scale factor, I'm going to say 10 is to 24. So I'm going to go 10 is to 24. And I'm going to divide by 2, and I'm going to get 5 is to 12. So this is dependent on if I'm going smallest to large. Most of the time, in this case, I'm going smallest to large. Most of the time, you'll be told, what are you doing? Are you going from small to large to small? And otherwise, if you're not told, then it could very well be 12 over 5. So we need to find x, y, and z. So let's find x first. So you're going to go left side is to left side. So you're going to go x is to 15 and now multiply by your scale factor. You don't have to. You can say as 10 is to 24. So meaning I can go x is to 15 as 10 is to 24. But because we already reduced 10 over 24, it just is a better option to use a smaller value, because then you just have to reduce less in the end. So we're going to cross multiply, and we're going to get 12 times x is equal to 5 times 15. And I actually don't multiply all this out. I'm just going to divide by 12 like this, and then cancel, and that makes 1. And then I have x equals. For this problem, 12, I'm going to rewrite that as 3 times 4, because 3 divides into 15 5 times, and that's it. So I get, what do I get? 25 over 4. And so some of these answers, you're not going to get, a nice little number. You might just get a fraction, and that's totally fine. The next number I'm going to find is y. So I'm going to say y is to 16 as 5 is to 12. I'm going to cross multiply again. I'm going to get 12y is equal to 5 times 16. I'm going to divide by 12 again, divide by 12. I'm going to get y is equal to, because these cancel and make 1. 12 I'm going to reduce to 4 times 3 again. 4 goes into 16 4 times. So 5 times 4 is 20. So I have 20 divided by 3. So that's what y equals. And lastly, in order to find c, okay, z, we're going to go z is to 12. So z is to 12 as 5 is to 12. And again, I can cross multiply and get 12z equals 12 times 5. But really, if my denominators are the same, then z is going to equal to 5. And I could set my numerators equal to each other. So determine if these polygons are similar. These are not similar because my sides are not proportional. So that's a no. These are not similar because my angles are not congruent. And lastly, two equilateral triangles, those are always going to be similar. Write and simplify a ratio of 15 days to 5 weeks. We did something like this a couple days ago, but the most important thing is this. So if I'm writing 15 days to 5 weeks, if I'm writing this down like this, one of the most important things is that in order for me to simplify any ratio, you have to have the same units of measurement. And so obviously days and weeks are not the same. They're not equal. So don't start canceling 15 into 5. You can't do that because in order to cancel anything or divide anything out, you have to have the same value. So I'm going to actually take 5 weeks and change that into days. So if 1 week is equal to 7 days, then 5 weeks is going to be 35 days. So that means I'm going to have 15 days on top. And I'm going to divide that by 35 days. And days will end up canceling because they are units of measurement. And I have 15 divided by 35. I'm going to divide both of these by 5, and I get 3 over 7. So simplifying this ratio is 3/7. Now remember, there's 3 ways that I could do that. I could write it like this as 3 to 7. I could say 3 to 7. Or I can say 3.7. And that's just that. Okay, so this one right here is the ratio of a model's car dimensions to the actual car. So see, this is a miniature. What is our dimensions of 1 to 56? It says the model has a length of 3 inches. So what is the length of the actual car? So in this case, you've got a ratio right here of 1 over 56. And it has a length. So how do I find the length of the actual car? So that's your unknown. So take a minute and I would pause the video and try to come up with, what your proportion is going to equal. And, of course, you're going to start with 1 over 56, but where are you going to put the 3 and where are you going to put your unknown? And that's what you're doing. You're saying you got a length of 3. Well, your dimensions are 1 to 56. So what's the actual length of the car? So if you take a minute, try to solve this and then turn the video back on. So hopefully you did that and you said, oh, it's 3 to some value here. Length is 3 inches. And what is the length of the model? So when you're doing this, you've got model. See, when you write models, cars, dimension. So sometimes it's easier is to write, there's my model and there's my car. Okay. So then when it says the model has a length of 3 inches, see the models go on top. So that's model. And then on the bottom, what's the length of the actual car? And so that to me is a little bit easier. And that's a huge hint to you is that, remember, your units of measure need to equalize on top and the bottom. They need to be the same. In solving this, I know I already have the answer here for you, but I want to remind you that you are going to cross multiply. And so 1 times x is x, and that's going to equal 3 times 56, and that's just going to be 168. And so that's the length of the actual car. So this is kind of cool. This is something that came up in The Lord of the Rings. I don't know if you're a fan of that or not, but so they used a lot of miniatures and to film Lord of the Rings. And they were like really detailed. And so one of the details was Sauron's tower, and that had a height of 8 meters and a width of 6 meters. So I like to, again, height width. So that tells me what I'm doing. Where do I put my height? So if I say height is my 8 meters and my width is 6 meters, okay, I want to, and then it says the width of the full size of the tower. So the width of the full size of the tower is 996. I know that goes on the denominator because that's also a width. Now I'm looking for my height, and that's what's unknown. So I feel like that's hopefully a little bit easier for you to know where to put what values. Remember, they all line up. If you go height is to width, then this is going to be height is to width. And the rest of this, these are going to cancel as meters. You're going to cross multiply. 6 times x is equal to 8 times 996 meters. And then, divide by 6 and then cancel. So you get x equals, and reduce that. I think it ends up to be what? 1328. Okay. So that's how you do that. Just make sure you line up your height and your width. So these are a couple questions of are the figures similar? And what we did in class basically is we said, well, two squares are always similar. 2 equilateral triangles, are they always, sometimes, or never? Equilateral triangles, when are they going to be similar? 2 rectangles, sometimes. 2 isosceles trapezoids, sometimes. 2 regular hexagons. Remember, regular means all sides and all angles are congruent, even though the lengths are the same, are different. So this one is an always similar. And a right triangle and an acute triangle. Now, if you remember what the definition of a right triangle is that it's a triangle that has one right angle. But the definition of an acute triangle means that all the angles, every single one of them, is less than 90 degrees. Okay, so I can't ever have a right triangle similar to an acute triangle because I'm never going to have the same. I'm never going to have a right angle. So that's a never. And then you could just check your answers here. Oops. Okay. And then I have more. What about 2 right triangles? Well, that's sometimes, because of course you could have a really long right triangle like this, and then you could have maybe, I don't know, an isosceles right triangle. So that would be definitely sometimes. 2 rhombuses, that'll be sometimes. 2 isosceles triangles, sometimes. Scalene, sometimes. But an equilateral triangle and another equilateral, they have the same values. So next, these 2 triangles are similar. What's their scale factor? So they told me that they were similar. Okay, they said that. And just for fun, I'm going to label these. I'm going to call this A, B, and C. And let's call this D, E, and F. And the reason I want to do that is I just want to remind you is how you would write this. You would say triangle ABC is similar to triangle DEF. And you have to say the right order. So like this works here, okay? But if I had said triangle BAC is similar to triangle what? If I go B up A over C, then this better be E up D and F. And then if I said, because similar triangles have congruent angles, then what would angle A be congruent to? So the angle A would be congruent to angle D. Okay, so just keep in mind that they do line up like we did in that last chapter when we had side angle side angle when we were doing proofs on triangles. So scale factor. Remember, I need the sides the same. So I can't go 10 is to y. I can't go x is to 21. But my scale factor, which I'm going to call SF, which scale factor, is 20 over 24. And so I'm going to divide by 4, and I get 5 over 6. So my scale factor is going to be 5/6. So when I'm finding x, I can go x is to 21. See, bottom is to bottom. Right? X is to 21. As 20 is to 24. Well, I just reduced that. So I'm just going to say as 5 is to 6. So I'm going to cross multiply 6x equals 5 times 21. I'm going to divide both sides by 6. And these are going to cancel. And I get x equals, 6 divides into 2 times 3. 3 goes into 21 7 times. So I get 35 divided by 2. And then that's what x equals. To find y, this is this side, and this side, I'm going to go 10 is to y. Remember, left is to right as left is to right. So 20 is to 24. So that's going to be as 5 is to 6. So we're going to have 5y is equal to 60, 6 times 10. I'm going to divide by 5 on both sides. So I get y is equal to 12. So we have something called angle-angle postulate. And what this means is if you have two angles of one triangle congruent to two angles of another triangle, then the triangles are similar. You know that the third angle is going to be congruent if you already have two angles congruent. If they're the same, the third angle has to be the same. Anyway, we call that the angle-angle postulate. Here's other postulates. You know, when we were proving triangles congruent, these are all the postulates we had. We had side, angle, side, 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 angle, side, angle, 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 side, and we had hypotenuse, length. But for each one of these, okay, you had to have the angles congruent and the sides congruent. You had to have both angles congruent and sides congruent. But for similar triangles, it's different, okay? You have side, angle, side. It means that the angles do have to be congruent. But remember what we talked about before, but the sides have to be proportional. So the sides are proportional. Okay? So it's really important that you distinguish that. Angles congruent, sides proportional. Okay? Meaning they're going to compare, you're going to ratio two of them, they're going to have equal values. So are these similar? Yes or so see the question mark. Are these similar? Yes or no? Remember, you need at least two angles. We have an angle here, because those are vertical angles are congruent. So this one would be, yep, angle-angle postulate. This one right here, this was very similar to one we just did earlier. We have angles here. We have these two lines parallel. These are corresponding angles, right? Also corresponding angles here. So that's a definitely yes. So something's wrong with this one. This is wrong, okay? So they're trying to ask you, why is this wrong? And it looks like to me that they, in order to find the scale factor, they went this side is to this base. And if you look at it, they went 6 is to 8. So that's not correct. The correct answer for this would be 6 is to 9. That's my scale factor. So if I divide by 3, I'm going to get 2 is to 3. So scale factor is 2 is to 3. So to find x, keep in mind I'm going to go x is to 8 as 2. Remember, x is to 8 as 2 is to 3. Now I could have said 6 is to 9, but I'm just reducing it. So 3x equals 16. So x is equal to 16 over 3. For this one, we're going to find the scale factor, small to large again, find x and y. And again, I just really want to stress, it's kind of important. Again, not everybody does this, but I personally do like to split up my triangles. So on the left side, I have 4, and I'm going to put my little congruent angles here because this is the small triangle that I'm peeling off like this. So I have 4, and then the long length is 4 plus 2, which is 6. Then I have the small length is y, and this is going to be y plus 3. And I know this is x, and that's 6. So we're going to go 4 is to 6. That's my scale factor. 4 is to 6. My scale factor is going to be 2 is to 3. Okay? Because I just divide it by 2. So we're going to go x is to 6. So x is to 6 as 2 is to 3. Cross multiply. I get 3x is equal to 12. I get x is equal to 4. Okay? To find y, I am going to go y is to y plus 3. So I'm going to go y is to y plus 3. And that's going to equal, now I could go x is to 6, which is 4 is to 6, which we already know, which is 2 is to 3. Cross multiply, I get 3y is equal to 2 times y plus 3. I get 3y is equal to 2y plus 6. And I'm going to get y is equal to, because I'm going to subtract 2y equals 6. And so y is 6. Okay, cool. Find the scale factor. Again, let's find the scale factor. The thing about this is this. This side here is going to match up with this side. And this side here is going to match up with this side. So, of course, y will match up with 9. But when you do your scale factor, you're going to say 3 is to 4.5. Now, you're not going to leave your scale factor like that because that would leave your answer in a decimal form, and you're not going to do that. So you would simplify that as 3 divided by, now 4.5 is 4 and 1/2. And that's what, 8 9/2? Okay, so we're going to fix that. See that? That's what I have right now. And what this says is 3 divided by 9/2. Well, that's actually 3 times the reciprocal. You multiply by the reciprocal when you're dividing, 2 over 9. And so 3 cancels into 1 over 3. So my scale factor is actually equal to 2 over 3. Okay, so that's an important way that you found that. So I'm going to find y first. I'm going to go y is to 9 as 2 is to 3. I'm going to cross multiply. I get 3y is equal to 2 times 9, and that's 18. I'm going to divide by 3. I get y equals 6. Okay. In order to find x, though, I'm going to go smallest to large. So 5 is to x. 5 is to x as, oh, I guess I should use a different color here. Let me do this. Okay, same color. 5 is to x. Where are we at? 5 is to x as 3 is to 4.5, which is 2 is to 3. And so we're going to get, and then we're going to get 2x is equal to 15, and x is equal to 15 over 2. And that's my answer. Okay, well, I hope that helped, this similar polygons. Okay, watch out for the quiz review. Thank you. Thanks for watching, and I hope that helped you.